The previous two methods of applying Bayes' theorem to screening test results were I hope you'll agree, reasonably straightforward. But sometimes you want to work out other results besides the positive predictive value. Well, then you may find it difficult to generalize the previous results. For example, you might want to know not the probability that a woman who has a positive test actually has a disease. You might want to know the probability that a woman who has tested negative has the disease. Well, how do you figure that out? That's not the positive predictive value anymore, although it's related to that quantity, of course. In order to work out screening test results like these in their, in general form, we need to study Bayes' theorem in its general form. Okay, so I'm going to break this down into a series of steps. If you simply follow these steps, you should be able to calculate the positive predictive value or other related quantities. The first step is to go ahead and define events, as we have done from the beginning in our elementary probability work. Define events of interest. Clearly, in the screening test example, there are a couple of events of interest. Whether or not the patient has cancer, I'm going to label B the event patient has cancer, and therefore B complement would be the event patient does not have cancer. And then there's also the event test is positive or negative. Well, those are two events. Well, let A be the event the test is positive, and let A complement, therefore, be the event that the test is negative. So define those events. Now, if you think about it, the positive predictive value is the probability of B given A, right? Because positive predictive value is the probability that the patient has cancer given that her test was positive. That's probability B given A. Now, let's go ahead, and we already know the sensitivity of the test, the specificity of the test, the prevalence of the test. Let's label those probabilities in step 2 in terms of the events we defined in step 1. What's the sensitivity of the test? That is probability A given B. It's a probability the test is positive when it's applied to people who are known to have the disease. So that's 0.8, that was given to us. What's the specificity of the test? That's probability of A complement given B complement, and that's 0.95. Again, specificity is the probability the test is negative, that's A complement, when it's applied to people who are known not to have the disease. So we're given B complement. And then the prevalence of the disease is just probability of B. It's the probability that a randomly chosen person from that population would have the disease. That's 0.015. That's just probability of event B. Turns out you're going to need to calculate a couple of other probabilities to apply Bayes' theorem in its more general form. One thing you'll need is the probability of B complement. B is the probability, if B is the event patient has cancer, B complement, the event patient does not have cancer. Clearly the probability of B complement is just going to be 1 minus the probability of B, using the rule of complements. That's got to be 1 minus 0.015 or 0.985. We're also going to need this one. This one's a little bit more complicated. Probability of A given B complement. We need, that is the probability that the test is positive given that the person does not have the disease. All right, well, that is just, now you have to get used to recognizing these. That's 1 minus the specificity. A given B complement is the complement of the event, A complement given B complement. Hard to say. Replay it a couple of times. Listen to it again here. A given B complement is the complement of A complement given B complement. Therefore, the probability of A given B complement is just 1 minus the probability of A complement given B complement. Now, if that's too many givens and complements, replace all of those events with their English language definitions, and I think it'll start to make more sense. A given B complement is the event that the test is positive given that the person does not have cancer. What's the complement of that event? Well, given that you have cancer, given that you don't have cancer, given B complement, only two things can happen. Either your test can be positive, that's event A, or the test can be negative, that's A complement, right? Therefore, those two events are complements of each other. Bottom line, probability A given B complement is 1 minus the specificity, 1 minus 0.95 or 0.05. Now, Bayes' theorem in its probabilistic form here, tells us that the probability of B given A, what we really wanted to find, that's the positive predictive value on the left-hand side, highlighted. Having trouble highlighting here, but that's as much. I can't highlight it. There you go. Probability B given A on the left-hand side of the equation. That is equal to the right-hand side, which has in the numerator probability of A given B times probability of B, all divided by this long denominator, which is probability of A given B times probability of B, divided by probability of A given B complement times the probability of B complement. Now I know you could go back to recording 1 and recognize that all of these 6 components on the right hand side, they are the sensitivity times the prevalence in the numerator, and in the denominator again you have the sensitivity times the prevalence plus 1 minus the specificity times 1 minus the prevalence. Yes, that is what Bayes' theorem tells us. Why this formula works out to be the way it is, well, that's explained in the lecture notes, which I know we didn't go over because we made that section optional, but I hope you'll go through those notes while you're reviewing Bayes' theorem here or learning about it. Try to make sense of it, and where it doesn't make sense, then hey, stop by my office. I'd love to go over the development of this Bayes' theorem formula with you. It just arises out of simple applications of the multiplication rule and the addition rule. Okay? All right, well, given that this is Bayes' formula, though, and we have all of these probabilities listed in steps 2 and 3, it's a simple matter to plug in and work them out. And of course, you get the same answer, 0.2. What's the advantage of using this uglier looking formula, but it's actually exactly the same formula as in the first recording? Well, here you can see that if you wanted to work out a different probability besides the positive predictive value, if you wanted to work out the probability that a woman has cancer given that her test is negative, well, that in terms of our defined events would be the probability of B, that's having cancer, given A complement. And that, that almost looks like what Bayes' theorem gives you a formula for. Bayes' theorem gives you a formula for probability B given A. If we want to find probability of B given A complement, guess what you do? On the right-hand side of Bayes' formula, wherever you see an A, plug in an A complement instead. Replace it with an A complement everywhere on the right-hand side. And then go back to the probabilities you know in steps 2 and 3, and you should be able to find them, if not directly by using rules of complements, you should be able to find all the relevant probabilities and plug into them. That should help you a little bit with the extra credit problem on quiz 1. Good luck with it, folks. By the way, once you get good at this, try out the additional practice problem on the 4th page of the Applying Bayes' Theorem PDF. The Bayes' theorem is not just for screening tests, it has wide applicability. And here's another application where Bayes' theorem helps you figure out the relevant conditional probability. I'm going to leave you with one last thought. In Bayes' theorem, if you want to look at it from the elementary probability point of view, as in this recording, the basic problem seems to be one that looks like this. You're asked to find, or it's of interest for you to find, a conditional probability, right? B given A is what you're trying to find the probability of. Probability of B given A. But if you go back to the known information, not all, but a lot of it seems to be in terms of conditional probabilities, but the given condition is the other event. Do you see what I'm talking about? We're wanting to find probability of B given A. But the known probabilities involve things like A given B. Or if not given B, then A complement given B complement. Looks like the B's and B complements are given in the known probabilities rather than the A's. And that's a typical situation for Bayes' theorem. You want to find a conditional probability. You seem to have similar probabilities of somewhat similar events, except that the events are reversed in terms of the condition. Okay? Think of Bayes' theorem when you think of problems like that. All right, have fun with Bayes' theorem, folks.